welcome to today's presentation. As you can see, today's topic is fatigue failure. Let's get started. Fatigue is a form of failure that occurs in machine components subjected to dynamic and fluctuating stresses. It is a common phenomenon in load-bearing components in cars and airplanes, turbine blades, springs, crankshafts, and other machinery, biomedical implants that are subjected constantly to repetitive stresses. It is often stated that fatigue accounts for at least 90% of all service failures due to mechanical causes. These stresses are often below the yield strength of the material, and when the stress occurs a sufficient number of times, it causes failure by fatigue. Invariably, fatigue failure involves some type of stress concentration in the machine component which act as the crack initiation sites. Design or manufacturing defects concentrate stresses and reduce the endurance limit, fatigue strength, or fatigue life. Fatigue is insidious and catastrophic, occurring very suddenly without any warning. A fluctuating stress cycle can be considered to be made up of two components, a steady or mean stress sigma m and a variable or alternating stress sigma a. The mean stress is the algebraic mean of the maximum and minimum stress in the cycle. Sigma m is equal to sigma max plus sigma min divided by 2. The range of stress is the algebraic difference between the maximum and minimum stress in a cycle. Sigma r is equal to sigma max minus sigma min. The alternating stress, sigma a, is 1/2 the range of stress. Sigma a is equal to sigma r divided by 2, that is equal to sigma max minus sigma min divided by 2. Stress ratio, R, is given by sigma min by sigma max. Amplitude ratio is given by the ratio of alternating stress to the mean stress, that is, I is equal to sigma a divided by sigma m, which can be simplified to 1 minus r divided by 1 plus r, where r is the stress ratio. Now we try to understand about the fatigue tests. Laboratory test for fatigue commonly employs a rotating, bending beam. During rotation, the lower surface of the specimen is subjected to a tensile, positive, stress, whereas the upper surface experiences a compressive, negative, stress. During one cycle of rotation, the stress at any one point goes through a complete sinusoidal cycle from maximum tensile stress to maximum compressive stress. In other words, stress cycle is reversed, sigma min equals minus of sigma max, that is, mean stress sigma m equals 0 and stress ratio, r equals -1. A series of tests at different stress levels are conducted to plot the SN curve. Number of cycles to failure at a particular stress is the data obtained in each of the tests. Engineering fatigue data is presented by means of the SN curve, a plot of stress S against the number of cycles to failure N. Fatigue tests at low stresses are usually carried out for 10 raised to 7 cycles and sometimes for 5 into 10 raised to 8 cycles for non-ferrous metals. The number of cycles of stress reversal which a metal can endure before failure increases with decreasing stress. A log scale is almost always used for plotting number of cycles N. The value of stress that is plotted can be alternating stress, maximum stress, or minimum stress. The SN relationship is determined for a specified parameter value of mean stress, stress ratio, or amplitude ratio, which is kept constant. It has been observed that two distinct types of SN behavior exist as depicted in the figure. For ferrous and titanium alloys, SN curve becomes horizontal at higher N values. In other words, the machine components sustain an infinite number of stress cycles without failure. The limiting stress level below which fatigue failure will not occur is called the fatigue limit, also called endurance limit. Most nonferrous metals, like aluminum, magnesium, and copper alloys, have an SN curve which slopes gradually downward with increasing number of cycles. These materials do not have a true fatigue limit. Fatigue failures typically occur in 3 stages. First, a tiny crack initiates often after sufficiently large number of cycles. Normally, nucleation sites are located at or near the surface, where the stress is at a maximum, and most probable sites are surface defects such as scratches or pits, sharp corners due to poor design or manufacture, inclusions, grain boundaries, or dislocation concentrations. Next, the crack gradually propagates as the load continues to cycle. Finally, A sudden fracture of the material occurs when the remaining cross-section of the material is too small to support the applied load. Thus, components fail by fatigue because even though the overall applied stress may remain below the yield stress, at a local length scale, the stress intensity exceeds the tensile strength. For fatigue to occur, the basic requirement is that at least part of the stress in the material has to be tensile. The fracture surface is perpendicular to the direction of the applied tensile stress. Now we will discuss about the characteristics of fatigue fracture. Fatigue results in a brittle-appearing fracture, with no gross deformation at the fracture. On a macroscopic scale, the fracture surface is usually normal to the direction of the principal tensile stress. A fatigue failure can usually be recognized from the appearance of the fracture surface. The fracture surface usually consists of two distinct regions. A smooth region, due to the rubbing action as the crack propagated through the section, top portion, and a rough region, where the member has failed in a ductile manner when the cross-section was no longer able to carry the load. The progress of the fracture is indicated by series of rings, or beach marks, progressing inward from the point of initiation of the failure. This can be observed in the smooth region. Beach or clam shell marks are normally formed when the load is changed during service or when the loading is intermittent, perhaps permitting time for oxidation inside the crack. Striations, which are on a much finer scale, show the position of the crack tip after each cycle. Beach marks always suggest a fatigue failure, but unfortunately the absence of beach marks does not rule out fatigue failure, since the loading can be non-intermittent. Failure analysis can be done by carefully observing the fracture surfaces at suitable magnification. The images of fracture surfaces are called fractographs. Figure A and B are fractographs of fatigue failure in steel rods. In figure, a failure originated at the top edge of the rod. The smooth area with clamshell markings in the top end corresponds to the slow fatigue crack growth. The larger dull, fibrous area is the fast fracture region in the ductile manner. In figure B, the crack initiated at a discontinuity in a thread. The slow crack growth region here occupies almost all of the whole fracture surface. The fast fracture area, lower right corner, consists of only about 10% of the fracture surface. Figure C shows fatigue striations imaged at higher magnification in beta-anneal T6Al4V alloy, which indicates the position of the crack tip after each stress reversals. This brings me to the end of my presentation. Thanks for your attention. Bye-bye.